Hello friends. Today's session is on data visualization using Python. My name is Prasun Kumar Gupta and I am a scientist with the Indian Institute of Remote Sensing, which is a unit of ISRO in Dehradun. So today we are here to talk about visualizing data. This is a very contemporary subject. It has many applications and a lot of research is being done in this field currently. With respect to programming, we are interested in making static or interactive plots. This could be in two dimensions or in three dimensions also. It may be an animation which is in space time in nature. And 2D plots also include maps. This is done primarily for exploring the data that we have. So, as an application scientist, you may be having a lot of field data or a lot of satellite data. How we can explore the data in Python, how we can find out outliers or whether any data transformations is needed in terms such that any frequency domain transformation or any time domain transformation or transformation in log or polar coordinates and so on. So if such kind of transformations are needed, we can only realize when we have plotted the data. And finally, the idea is to come up with certain model to fit the data, to uh, to do a regression or do some sort of modeling to be able to understand the pattern in the data and eventually be able to predict the output at an unknown space or time. This is a very, as I said, this is a very important subject and a lot of work is being done around this. Here I wish to share two literatures which talk a lot about how these maps or plots must be made. The first one is a book by Springer called Grammar of Graphics, written by Wilkins, which talks about what are the things that you should put on a plot and what should you try to avoid. What should be highlighted and what should be not highlighted as much. This is by the author Leland Wilkins. The second one is actually a image that we use or a rule set that we use for teaching how to make maps. These are called Burton's visual variables. So if you simply go on Google and type Burton's visual variables, you will get a chart sort of thing which tells that how you can uh, show size or how you can show or what of these qualities can be used on a map to show different things. So these are just to tell you that a lot of work is being done behind the theory of visualization. And in the market today, there are several softwares, a huge lot of them in the open source domain, like Python and its different modules, and a lot of them in the proprietary or licensed or paid domain. So, a very good example of a paid software which is very popular for visualizing data is Tableau and Power BI, which is a Microsoft product. Then, in the open source domain, ggplot2 has been very popular for a very long time. Then, in the web domain, if you want to visualize data on the web, D3 and its uh, its things in different programming languages like JavaScript and Python are also very popular. So, in terms of Python, again, there are many modules which help you visualize data. First and foremost is Matplotlib, on which we will be spending most of our time today. Apart from that, in the previous session, you may have seen Pandas, which is a very good library for reading data, analyzing data, and they have also borrowed things from Matplotlib for plotting purposes. Then there is a very good library called Seaborn, ggplot2, and a newer library called Altair. For mapping thematic maps using Python, there are again a set of modules. Folium, Basemap, Cartopy, and Iris are some of them. Then there are other visualization systems or modules in Python, such as Vega or Vega Lite, Bokeh, which is for interactive plots, Mayavi, which is for 3D plots, Plotly, and Paraview. Let's talk about Matplotlib. Matplotlib was first released by John Hunter, an American neurobiologist, in 2003. It is today the most popular 2D plotting library that produces publication quality figures in a variety of hard copy formats. So, if you have some research data, instead of making graphs and plots in Excel, you should try and attempt making it in Matplotlib so that it becomes publication quality. You can make various type of charts or plots using Matplotlib that includes line, scatter, bar, histograms, and pie charts. This is relatively low level. If you wish, you need not specify a lot of details, just the data variables which you want to plot. But you could add some effort and create advanced visualizations by adding more and more information about how you want the plot to look like. The best part about Matplotlib is apart from the standard plots that it can make, it has certain add-on toolkits which give it more power. For example, it has a toolkit called mplot3d which helps it make 3D plots. It also has an add-on toolkit called Basemap which is used for mapping and projection. Let us go to the website of Matplotlib and have a look at certain examples of what can be done using Matplotlib. So here you see there are certain examples of bar graphs, stacked bar graphs, grouped bar charts, horizontals. Then there are examples of plotting signals, multiple signals overplotted. There are examples of data being plotted in polar coordinates, then error plots, error subsampling plots, event plots, fractal diagrams, filled in areas, gradients, uh, with different line styles, with different marker styles, scatter diagrams, um, and so much more. The next library I want to discuss is about Seaborn, which is based on Matplotlib. It is a library which is derived from Matplotlib and built on top of it. It provides high-level interface for drawing attractive statistical graphics. It is primarily for statistical data visualization. Similarly, it is similar to the popular ggplot2 library in the R programming language. So here you can already see some of the examples which are made using Seaborn. You have your scatter plots along with the histograms. You have these filled line diagrams, uh, data with varying marker sizes based on certain quantities, projections, box plots, and more scatter and error plots. Again, the website of Seaborn has a huge gallery of different examples of data of visualizations that can be made using Seaborn. So you can see they have made heat maps, uh, QQ plots, um, contour plots, and these new type of visualizations, overlapping ridge plots, and so on. Bokeh is another such library which is primarily, or sorry, this is pronounced as Bouquet. Bouquet is another library which is browser based, although you could write it in Python, but the output comes in the web form. So you require certain understanding of web technologies like HTML and JavaScript. Uh, Let us go to the Bouquet website and also have a look at the different types of graphs or different types of plots which uh, a Bouquet can make. We will be working with Jupyter notebooks, so let us have a look at the ones which can be made on the notebook directly. Okay, the last module that I want to focus on is Folium, which is primarily for making thematic maps. This is when the statistical information that you want to portray also has a spatial component. There are many libraries which help you display spatial data, such as Basemap and Cartopy. The advantage that Folium has that it is built on a very popular JavaScript library called Leaflet.js. So it builds on the data wrangling strengths of Python and the mapping strengths of Leaflet to come up with very attractive maps. It has some built-in tile sets, built-in base maps as we call it, from OpenStreet, Mapbox, Stamen, others. And it also supports overlaying existing data in form of GeoJSON or TopoJSON. These are some of the examples which have been made using Folium. Here you see a basic map which has the OpenStreetMap as the background or base map. Here you see a map which is made using Folium and has the Stamen black and white toner as the background base map. These two images on the right show GeoJSON information or data which is overlaid with the base map, and this shows some information which is shown as a choropleth map or a data which is shown in different shades of green to emphasize on a base map. The few new libraries which are coming up are Vega Lite and Altair. They basically try to bring the grammar of graphics into programming. You can try this online using their online editor, or you can also install it in Python using Conda or pip by simply giving the uh, word Vega. Here I have given a link to a YouTube video. In this video, which is an introductory video to Vega Lite, they have shown all the different things which Vega can do, including making interactive visualizations by specifying the data and the way it should be shown uh, in a sort of a XML or you can call it a markup language. Uh, Lastly, there are many other such mapping and plotting libraries. Matplotlib is a very popular library. If you have used other visualization tools such as ggplot or others, it may come across initially as having not so many capabilities, but it is not true. It has many capabilities as we will see in the upcoming demo. There are many other packages like Chaco, GnuPlot, Biggles, etc. Many of them are not under active development, or they may be only maintained as part of a much larger project. For example, PyQWT is maintained as part of the larger package PyQt. And there is, in general, a trend towards web based technologies. Although Matplotlib can also make desktop based or, or standalone images as plots, and it can also make web based plots. So let us uh, now move towards some hands on using Python and Matplotlib. So now we will do the hands on on Python and see how we can visualize data using Python. So I assume you all have Anaconda installed. Anaconda is a distribution of Python which is freely available on anaconda.com. You can just go to this website and click on download now here. It's about a 600 MB file, and once it installs, you will see Anaconda 3 in your start menu here. So you just need to click on Jupyter Notebook. A prompt like this will open, some things will get printed, and you will eventually see a browser open up with the contents of your home folder. So on Windows, the home folder is C user and then the username. Then generally you keep the content on the desktop. So you go to desktop and you go to today's folder. You will see number of files. First is the notebook that we'll be working in. I have named it NWA PKG1. Then there are two data files. One is a netcdf file, air monthly mean, and the second one is sample rainfall runoff data.mat. These are the two data files. Apart from that, the rest are other files not pertaining to this practical specifically. So you just need to click on this IPYNB or IPython notebook. Earlier it was called, now it is called the Jupyter notebook. And you will see all the code which is written for today. So how we will do it is, I will run a part of the code, run one cell, explain it. Since you already have the notebook, you can download it from the same space, and you can pause the video and go through it yourself and try to understand what is happening. So let me make the font bigger. Let me just remove these toolbars and headers so we can see the full screen. Great. And we can see the I can remove the line numbers also. Okay, yeah, no, I'll need this line number for explaining. Okay, great. So what we have now is the Jupyter notebook and the commands. The first cell says import the required modules. As you know, you give the hash symbol where you have to give a comment. So I have one comment here. Then I have just left a space. This is not required. You can remove the space. And then I say import numpy as np. So I am importing a module called numpy. Numpy, as you know, is numerical Python. This is a very important module. And if you have not read about it or gone through some content on numpy, you must, because that is the basic module on which all these other modules are built on. So numpy is one of the most important basic modules that you must know. Then comes matplotlib, which is the star for today. We are going to see the capabilities of this module called matplotlib. Matplotlib has, as I said in the lecture, that matplotlib has several add-ons like my base map and 3D. So the 2D plotting module is called pyplot. Okay, so we will import only the 2D plotting module, matplotlib.pyplot, and give an alias to this, as whatever is written is called an alias. So instead of writing every time numpy dot function name or matplotlib dot pyplot dot function name, we give a short form to it, plt. So plt.plot, plt.show, and so on. Then we are going to use the SkyPy module. This is also built in your Anaconda. You don't have to install anything. We are going to use the IO module because we are going to use certain files. As you saw, we are using the netcdf file and the mat file. So to open this kind of special files, we'll be using this module SkyPy. and date time for some date time conversion. So how do you run? You simply click on the cell and you say shift enter. So it will run. You will see this asterisk sign come up here when it is busy, and once it is done, it will give it a number. So this is the first cell that I run. So let us start with making some simple plots. Let us start with making a simple sine curve. Okay. Or even before we do a sine curve, let's do a very simple plot. Let's say I want to plot this data uh, 3, 4, 5, 1, 2. Okay, I have an array which has 4 elements and I say plt.plot y. Okay, so what have I done? I have created a list, a Python list which has 4 elements, and I am saying plot that list. So let's run this. What do we get? We get a graph, our first graph. Now what does this graph look like and what does it have? So on the y-axis, you will see the first point 3, then the next point 4 is somewhere here, then the next point is 5, and then the next point is 2. Okay. On the x-axis, it has given the serial numbers starting from 0, 1, 2 to 3. Okay. So this is some information it has assumed itself. Okay. Now let me add one more thing. Let's say I don't want lines, I want dots. Okay. So I say plot y comma within single quote a full stop. So now instead of a line, you see just dots appear. Okay. So like this, you can give several arguments to this plot function. Let us have a look at the documentation of this plot function. How do you look at the documentation? Inside Jupyter Notebook, you just need to click write the function. Then after the parenthesis, after the bracket, just click there and you press Shift Tab once, then it will come like this, like a floating box. If you click there and you press it, I think 4 times, it will come like a box here. So it says plot is a function which plots y versus x. These are the different ways you can call it. And there are several arguments or parameters like format options. You can specify the color of these circles. So if I say instead of dot, if I say r dot, then these will become red dots. So by default it is blue. Or we can say k dot, then it will become black. K is for the letter black, R for red, B for blue, G for green, and W for white. These 5 colors are permitted. So then there are options like then there are many options. We will see those options one by one. So a very basic information I have added here and I am plotting it. If I also have some x and y, so let's say I have some x data also. My x data looks like this: 0.2, 0.1, 0.5, 0.6. And I want to plot x comma y. So instead of the computer generating the numbers 0, 1, 2 and 3, I am giving the x and y pairs. So my x and y pair is 0.2 comma 3, 0.1 comma 4, 0.5 comma 5, 0.6 comma 2. On a graph paper, how would you do it? You would draw the lines, you will label the x-axis. It is ranging from 0.1 to 0.6. The y values are ranging from 2 to 5. Okay, and then you will give those points individually. So let's see what the output looks like. See, the first point is at 0.1 on x-axis, on y-axis it is 4, that is this point. The next point is at 0.2, this point, 0.2 comma 3, so 0.2 on the x-axis, 3 on the y-axis. Then the next point is 0.5 comma 5, so 0.5 comma 5. And the next point is x is 0.6 and y is 2. Okay, so very transparent, very easy, and very simple to understand. What you write, what you get. You don't have to write any boilerplate code or have to write any extra statements than what is required. Now let us try to construct a sine curve. Okay, so what is the sine curve? You have some angles and you have the equivalent sine value. Okay, so these angles can be in degrees or radians. So right now let us take in radians. Okay, so 0 to pi, or if you want a longer x-axis, 0 to 2 pi. Okay, now numpy has a built-in value of pi. You don't need to write 3.141. If I just write np.pi, you will get the value of pi to certain number of decimal places. So what I want to do is I want to construct the x-axis starting from 0 up to 2 pi, and I want to create 50 intervals. Okay, so 2 pi is roughly 6.28 or something. 2 pi, 2 into pi is 6.28. So between 0 to 6.28, if I divide into 50 intervals, I will create what is called as a linear space or lin space. Okay, so numpy has a built-in function called lin space. It takes 3 arguments. One is where you want to start, where you want to stop, and how many intervals you want in between. Okay, so let's just run this one line x and let us first see what is x. So it says it is an array and it starts with 0, goes up to less than 6.28 or just, and there are 50 or 0, 1, 2, 3, 4, 5 and then 10 rows, 5 tens are 50 elements are there in this array. So what we have done is we've just constructed our x-axis values. Now we need to construct our y values. So y is nothing but sine of x. Okay, so I'm not, okay, let's write that y is equal to sine of x. Okay, and then what we want to do, we want to plot x versus y. Okay, so x is my angle in radians and y is the sine of all these values. So in numpy, if you run numpy.sine, if you run a function on an array, all the elements will individually get converted or get applied to that function and the output will also be an array. So let us look at what is y. Y, you will see it is a value which starts from 0, goes to 1, then reduces, comes down to 0, then goes to -1, and like a sinusoidal curve, the values will change. Okay, so let us, instead of seeing it in a text, let's plot them against each other and let us see the output. So here we have our second plot. This is nothing but a sine curve. Now if you see on the x-axis, the values are starting from 0, go up to 3.14 where it comes back to 0 and then goes up to 6.28 where it goes through a negative half trough and come back to 0. On the y-axis, the values start from 0, goes up to 1 and goes down to -1. Okay, but this is a very basic map. The idea of using Matplotlib or any other program-based visualization tool is to construct publication quality graphics or plots which can directly go as input to any journal. So to do that, you need to add decorations, as they call it. That is the labels, the x-axis label, the y-axis label, a chart title, some sort of legend, and more information like that. So we will see how to do them one by one. First, I am just repeating the same lines. X is equal to np.linspace 0 to 2 pi at intervals of 50. Line number 4 is plt.plot x comma np sine of x. So instead of now writing y as a separate variable, I am just saying plot x with respect to the sine of x. And now I am giving a new argument called label. I will come to why this label is required. Then I am giving I'm calling another function called x label. This x label will be applied to the x axis. The y label will be applied to the y axis. So it will simply write x on below the x-axis. It will write sine of x on the left of the sine of the y-axis in a vertical fashion. And the title of the plot will be sine of x. Okay. Now I am writing plt.legend, but how will it know what to write in the legend? By looking at the labels, of each plot function. So this plot function will generate one line, and that line will be labeled as sine of x. So let us run this and let us see what we get. So you see on the x-axis, initially there were no labels on x and y, there was no legend, there was no title. Now we have the x label x, the y label sine of x, the title of the chart, title of the plot sine of x, and a legend. Okay, so even if I change the color, let's say I plot it in red color now, it will make the corresponding changes itself. It will change the graph to red, and it will also update the legend to red color. Okay, you can adjust the title, you can adjust the y label, x label, anything you wish. Okay. Okay, next. Now what I want to do is I want to double the frequency of the signal. Instead of having only one curve like this, I want to have two curves. So what I'll have to do, I have to uh, make sine 2x. Okay. So instead of simply putting sine of x, now I am putting sine of 2 multiplied by x. The rest, everything is same. And now you will see that you have two curves. So that is because I have increased the frequency of the signal. Okay. So similarly, you can make it 3x, 4x. Depending on what you want to do, you can take your x and y values and plot them against each other. Okay. These are some data that we have created. You will get some data from the field. It could be something like temperature, precipitation, humidity, anything, and you want to plot it against time or plot it against each other, and you can get these kind of graphs. So now here I am giving you an exercise. You should review the code that we have done till now and try to find a code which plots the cosine of x. Okay, so pause the video here and try to plot the cosine of x. Now, I hope you were able to do the cosine of x. If not, I will tell you the code. It's very similar to the previous one. I will, with your permission, simply copy this code, paste it here, and say I will create the same x-axis. Instead of having plotting the sine of x, I will change it to cos of x, give it an appropriate label, change the y label appropriately, and the title of the graph. So now I have the cosine of x. Okay. A very interesting thing, if you noticed, that the legend automatically shifted its position from right to the left. That is because it tries to not overlap with any data on the plot. In case of legend, there is a additional parameter called location or LOC. Here you can write something like center and left and right and best. I think these are the four. Let's have a look at the documentation. I think there is one. There is one parameter called LOC, which takes these values upper left, upper right, lower right, or by default it automatically finds the best position. But if you wish to change it, you can do it manually also. So if I set to LOC or let's say lower right, it will change accordingly. Great. So now we know how to make simple plots. We know how to change the color, and we also one more last thing is how to change the width of the line. So color, you can write RGB, red, green, blue, white, that is W, and black for K. So these are the 5 colors which you can use. You can also use another argument called line width to increase the width of the thickness of the line. So you see here in the previous charts, a default thickness of 1 is used. You can change it to less than a decimal number, very thin, or to a higher number, a thick line. Uh, Replace G by G dot, GO, G plus to see their effects. So in this code only, just copy this code, paste it in this box, and in place of this character apostrophe G, you try to write apostrophe G dot or GO and G plus and see what difference does it make. So you can pause the video here again and see what changes that you get. So I hope you were able to run the code. Let me do it for you. I copied this code, put it here, and now I am writing, instead of simply G, I am writing G dot. So as you saw in the very first example that I showed you, a dot will create dots. If I write GO, it will create circles. And if I write G plus, it will put plus signs. Similarly, you could use more things like less than or greater than sign, and it will create these triangles and so on. So there are many such combinations. Depending on how you want to visualize the data, you can either change the color or you can change the marker type. Okay. Next set of decorations is printing text on the plot. So many a times you have a plot and you want to highlight something by writing on the plot. This is called annotation in terms of Matplotlib. And we will also see how to save the plot as a file in your computer. Okay. So again, we'll use the same sine of y example. So I have created a linear space. I am plotting the sine of y in gray color with let's say line width as 2, and I want to annotate that where the local maxima is happening. So when the x reaches pi by 2, that is around 1.5, the y is at maximum, that is 1. So at xy 1.5 and 1, I want this text local max to be written. So I will say plt.annotate some text and the location where that text has to be printed. And then I'm saying plt.savefig. So savefig is another function which will save the plot as a file, whatever name you give here. So I'm giving sine.png. So let me run this, and you see the same green colored sine curve has come and the text local max gets printed. So maybe there is some overlap if you want to increase y. So I don't want that to overlap. Let's say you print it at 1.2. So it goes beyond the chart. Okay. So we can also change the limits of your x and y axis. That is the next thing that I'll show you. So here you saw how to annotate, that is add some text, and how to save it. Where did it go? I saved it. So it goes to the same folder where your notebook file is kept. So I have kept it on my desktop. So on the desktop, I am seeing my notebook file and a new file which has got created just now, which is sine.png. If you double click on it, it is the same file that you have generated there. Generally, some journals will say we want the charts to be in certain amount of DPI, about 150 or 300 or 600. So that can also be set. There is a argument called DPI. So you say, now the figure is very small, I want it at 300 DPI. Okay. Now let's run this and let's see the output file now. So earlier you were seeing it was very small. So by default, I think 90 is the DPI it takes. Now we've made it to 300. So it is coming as a large figure. So this DPI argument is very important, especially when you are making plots for publication purpose. The last kind of modification with respect to linear plots are overlaying these plots. They are also called overplots. When you have multiple information, like you have point or line, you want some data which is absorbed from the field and some data which is predicted by a model, and you want to show them both on the same graph. So you have multiple series of data. So how do you plot them? There is no special command for that. You simply write the plot commands one after the other. So I am saying I am creating a linear space between 0 to 2 pi, and the first plot is sine of y and the second plot is cos of y. So I on the same plot I am having the sine of y and the cos of y. The y label I'll write as y, on the x label I'll write y, on the y label I'll say f of y. So any function that you have been applied on y. Since the labels have been written for both plots, the legend function will automatically generate the legend. And I am writing two new functions, xlim and ylim. So I'll come to that later. Let's just run this now and let's see what we get as output. So you see here there are two lines. One is the sine, which is shown in blue color, and the cosine, which is shown in the orange color. You may have noticed, and the x label is y and the y label is f of y. You may have noticed in the earlier plots, let any of these, there is some gap. It starts from little less than -1 and goes to little more than +1. So you can specify your limits of your x-axis. So currently x-axis is from 0, little less than 0 and little more than 6.28 also. So you can specify from where to where you want your x range, from where to where you want your y range. So to do that, we specify it using two functions, xlim and ylim. So plt.xlim, I want to limit it within 0 to 2 pi, and I want to y limit from -1 to 1. So now you will see that the y axis has been perfectly cut off at -1 and +1, and the x axis has been perfectly cut off at 0 to 6.28. Okay, now is the time to again revise everything that we have learned till now and apply those concepts to make this plot. So this is just an image. You have to apply all the things that you learned above to create this plot. Okay, so just let me give you a few hints. How many data sets we see here, or how many plot statements do we see here? We see one blue line go like this, another blue line come from the top, go to the bottom. So two plots there. One there is red, another is green. So at least 4 plot statements are there. There is one annotation origin, and you can limit your x and y axis, and of course the legend. So maybe 7 lines of code. So pause the video here again and try to revise what has been done till now and try to write code for this graph in the cell below. Okay, so let's see what the values of x are ranging from. I think the problem statement doesn't state, but the values of x are ranging from minus 5 pi to plus 5 pi. As you know, pi is 3.14. So minus of 5 pi is minus 15.7, which is somewhere here, and plus 5 pi is plus 15.7, which is here. So my x-axis values are from minus 5 pi to plus 5 pi. Similarly, my y-axis values are also from minus 5 pi to plus 5 pi. Let's try to make this line first, the x line. It is a very simple 45-degree line. So what can we say about this? It's a 1:1 line. Okay, that means the x and the y values are the same. So if I write x is equal to np dot lin space, I want to create a linear space from where? From minus 5 pi till where? Till plus 5 pi. How many intervals you want to give? This is up to you. Let's take 100 intervals. And the first statement is nothing but plot plt dot plot x comma x, and this has to be in the blue color, so let's write b, and the label will be x. So you see we have our first line. The next line is just the mirror image. So it is nothing, it is a mirror image with the mirror placed at the y-axis. So it is nothing but plot of x comma minus of x. Okay, so let's copy this statement again, paste it again. This is x with respect to minus of x. Actually the ints were given here only. What is x, what is the next line, what is the next line, what is the next line. So there are 4 plots: x with respect to x, x with respect to minus x, x with respect to sine of x, and x with respect to x sine of x. Okay, so let's run this. So I have my 2 lines, looks like a cross, very good. Next I want the sine x. Okay, so plt dot plot x comma sine of x. This has to be in green color. The label will be sine of x, and I see that the width is little more, so line width is equal to, let's say, 2. Okay, and if I run this, I will see the sine line. The last one is x sine x. So just let me copy this, paste it here. Plt x comma x multiplied by sine of x. This was in red color, x sine x, and a little more thicker. Okay, this is very much thick. Let's make it 4. Yeah, more or less the same. Then we have to annotate the origin. So we will say plt dot annotate. What is the thing that we want to, what is the string we want to put there? Origin. And what is the xy location? 0, 0 at the center. There you go. So I have my origin printed there. So I have my lines, I have my text. What do I need to do next? I want the legend, and I want these x and y limits to be set. So plt dot legend and plt dot xlim, x from minus 5 pi to plus 5 pi. Similarly, the y-lim or y-axis should also be limited to minus 5 to plus 5. So now you see the axes have been limited. Annotation is done. The lines are there. But the legend comes here. I want the legend on this side. So we will say legend location is equal to, what should be the value? Upper right. So now I have my legend on the upper right. So very good for those who have been able to do this. Now let us go further and let us see some more interesting graphs. As I told you, Matplotlib is a parent library and a lot of things can be done. May not be in one line, but a little more detail has to be given, and some very interesting advanced graphs can be made. So I am showing you some examples. These have been taken from a book called Learning Python, written by Ajit Kumar. He is a scientist at the Inter University Accelerator Center at New Delhi. So first is, if we want to plot, if we have a linear x-axis, we want to plot the x square and x cube lines. So this is how it appears. So what I'll roughly explain the code. First, I have made a range of numbers starting from 0.5 up to 5 at interval of 0.2. So minimum value is 0, maximum value is 5, and between 0 and 1 there are 5 values. So 0, 0.2, 0.4, 0.6, 0.8 and 1. Similarly up to 5. What am I plotting? This variable t, comma, on the y-axis it is t squared, t to the power of 2. So 1 to the power 1, 2 to the power 2 to the power 2 is 4, 3 to the power 2 is 9, 4 to the power 2 is 16, 4 squared, 4 squared, 3 squared, 3 3s are 9, 4 4s are 16. So this, okay, x is the blue line. So 16 and 5 squared is 25. Now if I want to print the plot the cube as circles, as red circles. So 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is 8 fours are 32, so on. So you can see x square and x cube lines. Now we will see also the effect of different marker symbols. As I was showing you, you can write dot or circle or plus sign, greater than, less than, then the caret symbol, or you could simply write x. So here I am also introducing you to the concept of subplots. Okay, so how are the subplots numbered? You have to just write plt.subplot, the row number, the column number, and the plot number. So this is row 1, column 1, plot number 1, row 1, column 2, plot number 2, row 1, column 3, plot number 3, row 2, column 1, plot number 4, 1, 2, 3, 4. This is row 2, column 2, plot number 5, row 2, column 3, plot number 6. So that is how this subplot numbering takes place. The number, row number, the column number, and then the plot number. And I am just taking 10 random values and first showing with x, then the plus sign, then the greater than sign, then multiplication sign, then the filled circle, and another triangle. So similarly, you can make x labels and y labels for each of them individually. There are also methods if you want to write the same y-axis for all, give only one label, or have the same x-axis for all and give only one label. All those kinds of possibilities are possible. So this code is just about showing the markers and showing you how the subplots are made. Also, this is an example to make a pie chart. A pie chart which has 4 synthetic data, 4 quadrants: hogs, frogs, logs, dogs, and each of them have a given percentage: 25, 25, 30, and 20. So you just have to write pi, the fractions of each quadrant, and the labels that you will give to each of the labels. So frogs is 25%, hogs is 25%, dogs are 30, and logs are 20. So logs takes the least amount of space. The next one is a polar quad. It's a polar plot. Very interesting design. Here you have 12 fangs coming out. How this is done? You create a space from 0 to 10 pi. You find the cosine, and instead of printing the cosine in linear space, you print it in the polar space. So you have 0 degrees, 15, 45, 90, 135, 180, and so on, back to 360. You can change this number k. So let's say I make it 24. That will increase the number of these circles around it. Or if you make it very small, let's say 4, you can have something like this. So this is an example of a polar plot. This is done using the plt.polar function. Then you can make some very advanced things like fractal diagrams. I will not go into details of this. Here they are using another function called imshow. Imshow stands for image show. So if you have any data which is in 2 dimensions, which can be made as an image, then imshow can show that data as a image like this. And finally, one small example of how you can make 3D plots. Again, I will not explain the example, but just to show you that these kinds of 3D plots can also be made using Matplotlib. Okay, now let's move on to the final part, which is, till now we've done everything on synthetic data. Let's try to use some real world data and see the direct application of this module on making some real world graphs. So I have 2 examples. First example is to show you how we can plot rainfall and runoff data. Generally, in a lot of research papers, you will see that they have rainfall on the primary axis and runoff on the secondary axis, and you can compare when the peaks of rainfall is happening and when the peaks of the runoff is happening. So here I am taking daily precipitation and discharge data for the period of 2005 to 2014, that is roughly about 3,600 odd days, from gauging stations situated near the University of Illinois in USA. I have the data set has 2 variables of interest: Q, which is discharge or runoff, and the unit is CFS, cubic feet per second, and R is rainfall. The unit is in inches. You can get the data from here, or I have downloaded the data and given it to you in this file, sample rainfall runoff data.mat. Okay, so I will, as I told you, I will use the scipy.io library, the Scientific Python's IO library, to open this data. .load mat is loading the file or the mat file into this variable called f. Now this mat file comes like a dictionary, so you can see the keys of the dictionary: header, version, global, QRT. The variables of interest are Q and R, the discharge and the rainfall. Let us have a look at the shape of this variable Q. We see that it is a 2-dimensional array. The first dimension, that is number of rows, is 3,653 and only 1 column. So it's a columnar data set. So I have my discharge values, but I don't have my date values. So I'll construct it myself. You can just simply Google how to create or generate a list of dates. So I found that I can use the date time library to give a base date, and then I can create a for loop starting from. Oh, that is why. Okay, now I know. So starting from 0 up to 3653, or less than that, 3652, and just add. So first I will add 0, so the same base date. Then I'll add 1 day, so it will go to 2nd January. If I'll add 3 days, 3rd January, 4th January, like that. If I add 3653 days, it will take me to the 31st of December 2014. Okay, so I am creating this variable called date list. It's a list of dates, and it has a length of 3653. It starts from 1st of January and ends at 31st of December 2014. Okay, so just let me print this date list. So it will print 3000 values, so it will fill my screen, but you will get an idea that it has created a list with multiple dates starting from 1st January down up to uh, 2014 December 31st. Now let us plot these two values, rainfall and runoff. So rainfall, you are seeing that the first plot, which is from 0 to 4 inches, and the discharge is from 0 to 175 CFS, cubic feet per second. But generally, in research papers, you will see plots like this on primary and secondary axis. Now, how can we make that in Matplotlib? So again, we will have to use the subplot function. Here I am making the x-axis twin, so I'll have two x-axis. The x-axis which will be used for plotting the first values, that is precipitation. The second one will be used to plot the discharge. So I'm first plotting date versus rainfall, and the next I'm plotting date versus discharge in blue color. Then I'm saying take the second one and invert the y-axis. So the y-axis, instead of going from 0 to 175, it is starting from 0 on the top, going down to 175. That is the purpose of this line. If I don't write this line, all the things will be overlapping and it will be very difficult to differentiate precipitation and discharge. So if I invert the y-axis of the second variable, this is how we can get. Then we set the x label to year, the first label to teleprecipitation, the second label to discharge in different colors, and here you have your publication quality plot. So you can save this and using the .savefig function and use it in your research paper. Again, you can pause this code here and try to zoom into the individual storm events. So you see high discharge points. You can estimate just by looking, okay, this is somewhere starting before 2008 and between in the somewhere around 2008. So you can change your X limits and try to expand the data between 2008 and try to inspect each of these storm events, try to understand the rising and falling limbs of the hydrograph. Okay, the last example is to show you how to make a basic contour plot. Now, the contour plot will generally be made using some underlying data. So let's say you have some temperature raster or you have some height points, some sort of data you have. From that, this first the contour lines will be interpolated and then they are displayed. So for this example, I am using the NCEP NCAR reanalysis data of monthly mean air temperatures, I'm just taking the first month data, January data, and I am going to make a plot of it, and I am going to put the contours on top of it. So this is 2D data, this is spatial data. This is there in this netcdf file, airmonmean.nc. This is again there in the folder for today. So I am using scipy.io, which is the library, scientific Python input output library, to read this netcdf file into this file object. From this file object, I am taking out the variable air, which is air temperature. This has multiple months data. I just want the first month, all the rows, all the columns. Okay. So I'm just taking the first month, the first band, converting it to a numpy array, putting it to a variable called temperature at time 0. Temperature units is again in a variable called units. I am converting it to string by writing this decode UTF. Similarly, I am taking longitude and latitudes, they themselves are two arrays. I am taking out those two arrays, longitude converting them to numpy array, and latitude and converting to numpy arrays, taking out the units of longitude and latitude and closing the netcdf file. Okay. That then using the latitude and the longitude values, I'll make a grid. So each of the grid points will have a lat and long value. Okay. Then I am using a contour f function to plot the temperature data using red color, and then contour function to make the contour lines around, or you can call it isotherms, lines joining points of equal temperature and showing them in the black color, color K. And then I am putting a label, X label, Y label, and then I am putting the legend. The legend here is called the color bar. This will be horizontal, and I am saying it is temperature in whatever units is it. So let me run this, and here you go, the final output, which is the monthly mean temperature of January for the whole world. Here you see it is starting from 0 degrees longitude going up to 360 longitude. So India would be somewhere around 66 to 96, somewhere in this area. So this probably is the Tibetan plateau and all. So yeah, you can see the temperature, and you can also see the isotherms as contours. They are also labeled 24 degrees, 32 degrees, 8 degrees, and so on, and minus as you go towards the poles, and along with the legend here. So this is how, this is just a small glimpse of all the capabilities of Matplotlib. Matplotlib is capable of doing much, much more. It is impossible to tell everything, even in multiple sessions. So I encourage you to try making plots using your own data. When you encounter errors or you want to know how to do this, try to search on Google, on Stack Exchange. You can email me and try to find, or put questions on the forums and our groups to get answers. This is the end of this session. Thank you very much.